Now, all this discussion about the recent improvements that we were seeing all around us, ranging from the technical ones like the adoption of virtualization or containers, scalability of services in public and private clouds, and also down to the actual software development process, where agile is the most adequate approach in this dynamic and ever-changing world. Well, all of this actually needs an additional type of glue, so to say, which is one of the recent additions to the technical world, especially to the DevOps environment. And that is a new buzzword called infrastructure as code. Now, the concept in itself isn't really that recent, because if you ever used a script, perhaps a bash script, a PowerShell script, to create some virtual instances in a public cloud, to interrogate something that's running behind some API, what you did was just infrastructure as code. So the concept behind IAC, or infrastructure as code, is about abstracting your virtual infrastructure using code, just like your application code. So what's the benefit of doing this? Well, first of all, you get error-free deployments. Once you have a code that describes your infrastructure and you have a smart piece of software that is able to understand that code and deploy it automatically onto a cloud platform, well, you can deploy that code as many times as you want, every single time completely error-free. So no more typos, no more forgetting about certain components, no more misconfigured security policies. And that's just one of the benefits. Other benefits come in when you think about the fact that with code, you can share it, you can reuse it, you can have a modular code where you can import different pieces of code written by somebody else and then reuse it in your own infrastructure. You can have that code in code versioning. You can check it in GitHub. You can perform code reviews. So pretty much all those benefits that were native to the software development world, now we get to enjoy them when we're managing cloud infrastructure. And that's infrastructure as code. Another benefit of infrastructure as code is your ability to now quickly destroy and rebuild entire environments, huge amounts of infrastructure, thousands of resources, anytime you need to. You might need to perform an infrastructure refresh. You might need to perform an upgrade to the infrastructure. All that now can be done just by changing a couple of lines in your code file that describes your infrastructure. Even more than that, let's say at some point you have a development environment and you want to create a test environment which is identical to that one. Or you have a production environment and you want to make some tests before upgrading that application that's running in there. You can instantly create an identical environment based on the same code files in a matter of seconds or perhaps maybe a few minutes. So that's how flexible infrastructure as code can be. And it's free. It's all the tools available out there that can do infrastructure as code. Most of them actually are free and can be used by anyone. And if you still aren't convinced yet, here's another benefit of infrastructure as code. It's the ability of avoiding situations where you end up with so-called snowflake systems. That is, identical systems which initially might have been configured identically. Those are the systems that don't exactly match the configuration baseline of all the other systems out there. So you might have had a bunch of servers that were initially configured the same way, but perhaps some updates were performed in the meantime. Perhaps somebody else came in and performed some manual changes in the configuration of one of them. And this is where bugs and errors start to appear. We call these snowflake systems because they are customized in a way that cannot be easily reproduced. So whenever you need to rebuild the entire infrastructure, you're not going to be able to reproduce the exact same steps that ended up building that initial snowflake system. So we don't want snowflake systems. We want uniformity. We want everything to look the same so we can manage all those systems at once using the same policies, using the same approach, and to have some sort of predictability in our infrastructure. Infrastructure as code avoids these situations because everything has to be written in that code. There's no approach in which an admin now connects to a remote instance, to a virtual instance, and starts messing up things in there and updating packets and changing configuration files. No, everything now has to be done in code, and everything has to be monitored and centralized in that piece of code that manages your entire infrastructure. You need to update something? Sure, make a change in that code that represents the infrastructure. You want to update to a newer version, your new application, use a different image, use a different container image, you use a new image for your virtual machine, but destroy the infrastructure and rebuild it from scratch. Unfortunately, all the cloud vendors out there are very, very friendly to this approach. You might be wondering, well, why do you keep saying, I don't know, destroy and rebuild the infrastructure? Why do I want to destroy something that's working? Well, destroying and performing an infrastructure refresh is always a good idea to avoid situations such as snowflake systems and configuration drift issues. And as I said, for cloud providers are extremely friendly to this approach. That's exactly what we're doing with containers whenever we're updating the application inside of our containers. We're not connecting over SSH to them and performing an update. No, we're just destroying those containers and reinstantiate them from an updated image. That's exactly what we can do with the entire infrastructure that we're managing, not just with containers. And the infrastructure as code allows us to do so. Another feature of infrastructure as code is called idempotency. You might pronounce it differently. I pronounce it idempotency. It's the ability of applying the same script, the same code multiple times without adversely affecting the initial apply of that code, the initial deployment. Think about a script that creates some infrastructure and configures perhaps some virtual machines, just a simple bash script, right? If you run that script twice, intentionally or even by mistake, what's going to happen? Well, more often than not, something bad is going to happen. You're going to end up with duplicated infrastructure. At worst, you will end up with some resource collisions in there, maybe resources that cannot have the same name at the same time, and a lot of issues such as these. Now, infrastructure as code has the ability, using this idempotency feature, to be able to memorize, to store the state of the infrastructure, so that when you happen to apply the same code a second time, it's going to be smart enough to figure out, well, has this infrastructure already been deployed? Has it been partially deployed? Or hasn't been deployed at all? And it's going to decide what exactly needs to be done to bring that infrastructure to compliance, to match your configuration. And among the tools that we can mention here that allow us to implement infrastructure as code, my personal favorite is Terraform, because it doesn't tie you to a specific cloud provider. You can talk to any cloud provider out there. We also have similar features and similar utilities from major cloud vendors, but most of them work with only their own cloud infrastructure, such as AWS CloudFormation or ARM templates in Azure Resource Manager. Another concept closely related to infrastructure as code is the concept of microservices. But before we get there, let's see how did we actually end up with an approach that looks like what we currently see as microservices. And that approach started from the very beginning of software development, back when the development of applications was like the development of a monolith, huge block of code. Everything was in one single binary file. Any change that you were supposed to be performing in that code meant a rebuild and a redeployment of the entire application from scratch. We did this for many years because we didn't know anything about agile development. We didn't have app stores that were able to push an update to our clients maybe 5 times a day. And we honestly, most applications were designed to work for many years without any intervention, and perhaps sometimes even without any updates. So it was okay for a while ago, many years ago. Nowadays, things are much more dynamic. So nowadays we tend to go ahead to stray from that monolithic type application and move towards a modular approach when developing application. And this modular approach started as a service-oriented architecture. Now, just like the name says, it's an approach in which we are trying to split the functionality of a larger application, the old monolith that we had before, into discrete and separate components. And each component is supposed to do one single thing and do it very well. And also, those components should be closely mapped to their business requirements or to their business purpose. That's why we call it service-oriented architecture, because it's an architecture built on a couple of modules in which each module provides a single and very well-defined service. All of them together, taken together, and ensuring communication between them is what makes our large application work. So basically splitting the application into multiple smaller applications in which each component does one single thing and does it very well. Now, in order to abstract this functionality and not create an additional layer of complexity, we are defining each subcomponent, each service in here as a mini black box, which only has a couple of inputs and a couple of outputs. We only know what that black box is supposed to be doing. It knows what type of inputs it's expecting. We know what type of outputs we're supposed to be getting back from it, and that's it. The only thing left to do is now to connect those inputs and those outputs in order for those services to be able to communicate among them. And since those subcomponents only rely on those inputs and outputs, it means that they shouldn't rely on the state of other services. So they should be designed in such a way so that they shouldn't even be aware of the state the other services are in. They're simply waiting for input and they're providing output. That's it. It also provides us with the ability now to perform independent upgrades. That is, whenever a part of the application needs to be upgraded, let's say the front end, or let's say we need to add a new authentication mechanism. Maybe we need to connect our application to a different storage service in some cloud. It's just a matter of upgrading a specific component in that service-oriented architecture. We don't really need to build or rebuild and reship the entire application from scratch like we used to. And it's even code independent if you think about it. I mean, having each component running in an independent manner and only expecting some inputs and providing some outputs basically allows us to develop that component in any language that we want. We might even have an application that is written in 5 languages. Each component, one of them is developed in Java, another one developed in Python, another one is just a script, another one might be C or C++, another one might be .NET, whatever you want, as long as they still communicate using the same protocols and the same language. Which is great for larger projects and huge teams that are working with a multitude of and a variety of expertise on the same project. And as you can probably guess, having these separate components communicating among each other, well, creates a bit of a complexity in that communication channel as well. You have to make sure that you're kind of designing something like a network in there with firewall rules and everything else that allows or disallows specific components to communicate with each other. And some specialized products have emerged on the market that only deal with this topic here, the communication mesh between these components in service-oriented architecture. And finally, we kept talking about service-oriented architecture, but actually what we've been describing, at least 90% of it, is the concept of microservices. Now, there are slight differences here, which pertain more to the philosophical nature of their description, but long story short, a service in a service-oriented architecture is considered to be a service that can also be developed as part of multiple sub-services. So we can have sub-services that create one service, which in turn becomes a component in a larger application. That's just the concept here. With microservices, we consider these services to be atomic, so there's no sub-service component in a microservices approach. And again, this approach shares many of what we just talked about, the philosophy of service-oriented architecture, the philosophy of Unix, in which each and every piece of software does a simple thing and does it very well, the fact that they should be completely decoupled. Even more with microservices, we like to refer to them as being highly decoupled, so we have a complete independence between these components. While with service-oriented architecture, we call them loosely decoupled, where they might have some additional dependencies among them, such as, the hierarchy between a service and its sub-services. And when you have such a highly decoupled architecture, an infrastructure, basically, we also need some sort of a high-level overview and control over it. This is where we find the term orchestration. Orchestration in itself has been slightly abused recently, and all the vendors out there brag about developing their orchestration solutions. But in essence, orchestration means a sort of high-level control and overview over a more complex infrastructure. Orchestration allows us to define workflows. As in, instead of simply saying that, well, we need to create a virtual machine, and then we need to, attach some virtual network interfaces to it, and then connect those VNets to some subnets, and then configure some security policies on those subnets. Well, orchestration could abstract an entire huge process of deploying and configuring infrastructure as a single task. So that task might be add a new web server instance to the front end of our application. Scale our front end by 1. which means in the back end that that orchestration process is going to take care of choosing an image for the virtual machine, deploying their virtual machine, choosing the hardware for it, configuring the networking for it, configuring the security policies, attaching storage to it, configuring some heartbeat protocols to make it become part of the existing cluster. So all that sequence of tasks now can be abstracted into a single action. And whenever we're deploying that action, we say that we are performing orchestration on top of that infrastructure. Obviously, this is the next level in automation. Some people call orchestration as automation of automation. So we might have discrete scripts or discrete instructions and pieces of code that create a virtual machine, that create a networking part, that create a load balancer perhaps. If we automate the deployment of those scripts, so we're basically doing automation of automation, that's when we might be calling it orchestration. Now, if you think this is cheesy, yes it is, because it's marketing actually. Some tools worth mentioning here, the go-to DevOps tools for configuration management and infrastructure management. And I would mention here, at least for your general knowledge, if not even for the exam, I would mention Ansible, Chef, Puppet, SaltStack, and even Terraform. And of course, don't forget, if you're going to the container world, we have the one orchestration solution to rule them all, which is called Kubernetes. You might also be using something like Docker Swarm or even Helm on top of Kubernetes. Now, we've mentioned that all of these services, it doesn't matter if it's about service-oriented architecture or the microservices approach, they all need to communicate with each other. And if you think about it, it's not just the inter-service communication that needs to happen, but also the outside communication of your application that needs to happen. So pretty much all these interfaces nowadays between the services and between the application and the outside world are going to be performed over APIs, application programming interfaces. And we have about two, let's say, styles or flavors for implementing these APIs. We have the older SOAP representation, Simple Object Access Protocol, which is based on XML messages, and can also be extended according to the specifications of the web services standards in order to attach additional functionality to it, such as authentication, encryption, the way errors are handled, and so on. On the other hand, the more recent one is REST, Representational State Transfer. You might have heard it as a RESTful API or a RESTful approach, which uses the traditional HTTP methods and verbs in order to interact with API endpoints. And all the resources that are being referenced through a REST API are basically abstracted as URLs. Another more recent approach to computing, introduced by most public vendors out there, cloud vendors out there, is called serverless computing. Sometimes also named Function as a Service, FaaS, which is unfortunately very confusing, because when you call it serverless computing, you think about the fact that you are able to run some code to perform some computing operations without relying on a server, which is of course extremely not true, because you do need a server, you need a CPU, you need some memory, you need an operating system, you need an interpreter, you need something in there to run your code, to run your application, even though you don't get access to the underlying infrastructure. So serverless computing or cloud functions are a service that allow you to bring your code, perhaps a small piece of code, kind of like one single microservice, let's say, and then run it in a short-lived container. You're basically attaching that code to some sort of an event. So whenever that event fires, whenever that event happens, let's say, for example, an application requires to interact with that service. Maybe a file gets uploaded, maybe some other type of event happens in your application, then that piece of code is immediately run in a short-lived container, and after the run is completed, the container is destroyed. Now, why is it called serverless computing? That's because you're not ever going to see anything related to the infrastructure that's used in order to run that code. So you're not seeing the container, you're not seeing the container engine or the hypervisor that's running underneath it. You know nothing about the actual hardware. You only know that whenever that code needs to run, it magically runs somewhere in that cloud environment. We do have many advantages to this. Of course, first of all, we don't care about the infrastructure. We just know that whatever code we're putting in there is going to run. And of course, we can even develop entire applications based on cloud functions, in which each cloud function is actually a microservice, and they start talking to each other, and they start synchronizing, and they start delivering a service as a whole, and that's an entire application. Another advantage of this is the fact that you are able to pay only for as long as your code is running. So if that code takes a millisecond to run, you're going to pay for that millisecond and that's it. If it takes 10 minutes to process a huge video stream perhaps, then you're going to pay for those 10 minutes of execution time. If your code is never used, you're never going to pay for it. And guess what? Securing that code is your responsibility, because it's you who is actually pushing the application on the components of that application to be executed in that managed environment. Of course, the cloud vendor has nothing to do with what your code is actually planning on doing. So if you have flaws in your code, if you have vulnerabilities in your code, those are going to be yours to manage and to try to fix. The cloud vendor, on the other hand, is going to always take care of making sure that the infrastructure behind those functions is always up and running and is always able to run the code that you're providing. So back to infrastructure as code. And these are basically the things that we've already covered in the introduction slide. So we already know that infrastructure as code allows us to abstract our infrastructure using regular code, just like your application code. There are actually two approaches to this. So we can use that code to either manage the actual infrastructure, as in create the virtual machines, create the networking, create the storage appliances, create the load balancer, create whatever you have in there, and that is infrastructure deployment. And you can also use it for infrastructure configuration. That is, what do you do with those resources after you have deployed them? I mean, you have created a virtual machine. That's great. But what about, creating some users on that virtual machine, maybe installing some packages, maybe configuring them, maybe starting some services? So we have one deployment part and we also have one configuration part. And we have tools that are best at either one of these abilities. So for example, Terraform is going to be a great tool for deploying the infrastructure. It's not going to be the best tool out there for configuring the infrastructure. But for configuration management, we have tools such as Chef, Puppet, and Ansible. And we said that among the greatest benefits of IAC is the fact that it makes no typos, it's fast, it's predictable. It also provides us with state knowledge, that is, ensures idempotency. Whenever we apply the same configuration twice, the tool is going to be smart enough to know whether that infrastructure needs to be deployed or not. It also becomes a great way to validate that your infrastructure still matches your desired config. That is, if you try to apply a configuration in infrastructure as code again, and the tool such as Terraform tells you that no changes need to be done, that's a confirmation for you that there are no configuration drifts happening in there. There are no snowflake systems, and they're still compliant with your desired config. And don't forget that you can also take this approach the other way around. That is, if you need to perform an infrastructure audit or a security audit, you don't really need to hunt down all the resources anymore and find out what the configuration for each and every server is and each firewall rule, because everything is already in the code that you're using to deploy the entire infrastructure. You just have to review that code by your human eyes or by an automated tool, and there you go. That's the source for your infrastructure or your security audit. And by the way, just to give you a short idea here about how infrastructure as code looks like, here's an example here from Terraform, which by applying this small piece of code right here, this resource definition is going to create an instance inside AWS, inside Amazon Web Services. Now you can see that the code itself is not really difficult to read. I mean, we have a resource definition here, we have an API type, this is how we call the API, and we tell it what type of resource to create. We give it a name here, just like any object name out there. We specify an AMI. If you ever played with AWS, you probably know that an AMI is just the image that we're using to launch an instance, a virtual machine. In our case, it's going to be an Ubuntu release. You can see it right here. It's extracted dynamically from the cloud using a data source. And then we have an instance type that says T3 Micro. Now, this is the actual hardware of the virtual machine. T3 Micro, if you Google it up, is going to show you that it's a very small shape of virtual machine with just one single CPU, 1 or 2 gigabytes of RAM, low networking bandwidth, and other cheap stuff that we can easily instantiate without paying too much for that instance. Also have a couple of tags in here, and that's pretty much it. This piece of code right here is the one that is going to create an instance based on this code onto AWS for us. Now, you might be wondering, okay, isn't that too simple? I mean, where's the networking part? Where's the security? Where's the storage? Well, of course there is. Of course, you do have the ability to configure that. And if you scroll down here, in this AWS documentation page, you can see that we have a bunch of additional configuration fields that we can attach to the instance definition. So basically, whatever you can configure through the Cloud Console, right, of any public cloud provider out there, you can configure it as well using the API. And through the API, you can use tools such as Ansible or Terraform to perform this in an automated manner for you using infrastructure as code. Finally, software-defined networking is another topic that plays extremely well with, everything software-defined, with automation, with orchestration, with cloud environments, with scalability, with elasticity, with all the things that we've gotten so used to since we've invented the cloud. Now, software-defined networking is exactly what it says, is networking features and networking functionality such as switching and routing and firewalling and security rules and perhaps even traffic inspection and everything that you're normally doing in a physical network, but now performed solely in software. So we have virtual links, we have overlay networks, we have virtual firewalls, we have virtual switches, we have virtual routers, and everything is running as a virtual machine or as a container onto our computing infrastructure. Now, of course, we still need physical boxes and physical cables because we still have physical servers, even though they're virtualized, right? So we still need some layer 1 devices in there to be able to actually push those packets around the network, around the physical network. So what actually happens here is a paradigm shift from the traditional method of managing networks and designing networks, where all the functionality was built into one single box. Now, we had a router that had some interfaces on it. That's where we defined the routing protocols. That's where we defined the access lists. That's where we were defining authentication policies, perhaps, for users connecting to the network, and so on. Now, we're moving all that intelligence into a centralized control plane, which is actually just an application that is running on a dedicated server. And for the actual packet pushers, for the actual devices that we need them to transport those packets, we can use some simple, very fast and dumb devices that don't really need any intelligence into them, but they know how to listen to whatever instructions are coming in from the control plane. All right, so we're grabbing all the intelligence from our dedicated networking appliances. We're centralizing that intelligence into a large brain that knows everything about the entire network, and we leave those small devices in there, those switches, to just obey the instructions that are coming in from the control plane. And we call that the data plane, right? We only need some very fast switches. We don't need them to be very smart. We don't need them to be able to inspect traffic, to apply complex security policies, because all that effort is now being done in the centralized control plane. On top of that, you might have a management plane, but this is just a concept more than an actual component. That's the actual interface that the admin is interacting with whenever they need to make some changes in the configuration of that network. Now, having everything defined as a configuration file or as a virtual policy in that control plane allows us to perform very quick changes in our network, to reconfigure the network in a matter of seconds, and to perform some automated responses perhaps in the network as well. Which brings us to a discussion about what do we do when a security incident happens. Well, with software-defined networking, it's so much easier now whenever you're detecting an intrusion attempt in one edge of the network to quickly react over the entire network and quickly deny traffic for the affected host or for the affected malware destination that was just detected over the internet. So you could have some sort of a quick response mechanism that quickly starts protecting your network, something that you couldn't have, or at least not at this level, with physical devices that needed to communicate among them and needed to synchronize them. And they had to talk to each other even though they might be from completely different vendors that weren't designed to cooperate. And as a concept here, just to get the terminology out of the way, normally when we talk about SDN, we're also talking about two paths of communication between the components involved in an SDN architecture. So between the physical devices and the SDN controller, that is the actual brain of that SDN deployment, we call that southbound API. So remember that for the exam as well. On the other hand, between the SDN controller and the management layer, the one that you as an admin is going to interact with, well, that is considered to be the northbound API. Notice that we're still talking about APIs here. right? That's because SDN is also a type of, well, quote-unquote application, actually, that can be easily managed in a programmatic way. It's actually designed to be managed programmatically because it's designed to be completely automated. And it's designed to eliminate all that manual management effort that you had to perform up until now by SSHing into all those routers, all those switches, and propagating VLANs, and updating access lists, and checking to see how the traffic flows, and why doesn't it reach that destination over that link, and why does it use that link, and all that CLI configuration hell that you might have experienced before. And another term here, which again, it's more like a marketing term, it's called NFV, Network Function Virtualization. It's basically what we just said, what we just talked about, but its official definition is that NFV is whenever you are starting to deploy network functionality, such as routing, switching, firewalling, intrusion prevention, whatever you might have, load balancing, whatever you might have in that network, as a dedicated virtual, either appliances as virtual machines or as containers. And since we're in the marketing area, let's introduce two final terms in here. Those are fog computing and edge computing. Now, fog computing, it's like a cloud, but it's not exactly a cloud. Hasn't yet become a cloud. No, I'm kidding. It pretty much has nothing to do with a cloud. Fog computing is a term that is often found in IoT deployments, Internet of Things, right? Sensors deployed all over the place, all over a field, a parking lot, a park, a country even, and all those sensors are generating a bunch of data. Now, all that data might not be feasible to be backhauled over, Zigbee, or down to a gateway over 4G or 5G, and then over physical links, and then over IPsec, all the way back to the data center where the IoT application is located and where the data should be analyzed. So what we're doing with fog computing is that we're placing some specialized, a bit higher powered nodes among those IoT devices that are being used as gateways. And those nodes are going to gather the statistics collected from all those sensors. They're going to perform some local computation onto those statistics, or perhaps summarize them somehow, or normalize the inputs some way, so that with less frequency and with already prepared data, they will periodically send those statistics, send that data back to the data center. So we are offloading a part of the data processing effort right next to where those sensors are located, so that we're not receiving a bunch of gibberish and a bunch of useless information, but we're only receiving actionable information from those sensors, which is already processed by those fog computing nodes. What about edge computing? Well, it's pretty much the same thing. It's actually a superset of fog computing. Nowadays, we consider fog computing as belonging to the category of edge computing. It's just that fog computing was a term invented and coined by Cisco. From a security perspective, edge computing, fog computing nodes are going to be the #1 target for attackers, because these are the first devices that are actually connected to a real network that can be reached from the internet or from some private network, but they do have real network connectivity, which means that they can become a high-value target for data exfiltration attacks or for denial of service attacks. So I hope you enjoyed the discussion. This is one of my favorite topics, and I really hope I managed to stir some interest and make it fun and interesting. So thank you so much for watching. Like, subscribe, support the channel if you wish, if you can, and see you on the next video. Bye bye.